end up getting the momentum is like minus here, and that's heading the wrong way. So you've got the wave going that way, the particle going that way. So that's not physical. So you want so you choose to have a minus here to make it physical, right? So so for that momentum, whatever it is, you get wave functions that are plane waves of this form. Okay, they're your eigenfunctions here. Now, are those eigenfunctions orthonormal? Right, they need to be orthonormal. That was one of the requirements. You know, we talked about that at length in the case when energy was the observable. So how about for momentum? Are the momentum eigenfunctions orthonormal? So like if we have two different momenta, p dashed and p, so two different eigenfunctions, u p dashed and u p. So if we take the bracket, if p dashed and p are different, do we get 0? And if they're the same, do we get 1? Well, this bracket you can write in terms of the integral form, you know, the overlap integral form. And I've put it here, homework. You do this for homework. So if these are your, that's the form of your eigenfunction. So you put in two of them, k and k dashed, and you'll get something of this form. Okay, and overall, let's talk about one dimension for the moment. So it'll be 1 over L. This is the three-dimensional version. But you know, keep it simple. Talk about one-dimensional wave functions. So you've got a wave front just heading that way down the x-axis, let's say. Okay. So your limits for x now are just 0 and L. Talked about that before in chapter 4 to solve the normalization problem. Okay, so go back and revise if you've forgotten. Okay. Now solving this is pretty trivial. You just get this. Okay. Now a bit of revision from chapter 4 as part of the solution to the normalization problem. We said in one dimension x, we imagine the x as a very large circle of rate of circumference L that's cycled. So your wave function at x plus L should be the same at x, and given that restriction, we proved this, that e to the I kl has to be 1. I haven't put in all the lines. You know, there's a jump from this to this, but go back to chapter 4 and refresh your memory if you need to. But anyway, what we're going to need is this ei to the kl, and L is this repeat length, if you like. So we'll need this e to the I kl is 1. Now it doesn't really matter what the k is, it's the L that's important. So e to the I kl is just the same thing as e to the I k dashed L, and it equals 1. Alright? So if k and k dashed are different, then you'll get here e to the I kl times e to the minus I k dashed L. Now they're both 1, right? they're both 1. So then you've got 1 minus 1 is 0, and therefore they're orthogonal. So if p dash and p are different, this becomes 0, and therefore the bracket here is 0. So that they are orthogonal. Okay, now when p dash and p are the same, does this bracket work out to be 1? Well, when you evaluate this integral, you get this. Now let p dash be very close to p, in the limit, and we'll let it equal p. Have a look at this exponential here. Now I haven't written it all out. I'll just say it verbally a little bit. Now e to the I, this stuff. Just think of it as I don't know, s. So you've got e to the s. Now expand out e to the s. E to the s is 1 plus s squared over 2 plus s cubed over 3 factorial dot 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 dot. Okay? So if you expand this out, you'll get 1 plus I, well, you know, this, you get this. So it'll be 1 plus I k minus k dash L plus all this squared divided by 2 plus all this cubed divided by 3 factorial, so divided by 6. Now, okay, now when k and k dashed are almost the same, the square of it is a much smaller number than k minus k dashed, and the cube even smaller. So you can neglect the square terms and the cube terms and so on. So effectively all you're left with is 1 plus this minus 1. Well, the 1's cancel, and then all you're left with is I into k minus k dashed L. Well, that's what you've got here, except for the L. So the L's left. These two, you know, the I, k minus k dash, they cancel, and you're just left with the L. You've got an L outside, so the whole thing just becomes 1. Okay? So therefore the bracket here, when p dash equals p in the limit, is just 1. Okay? So it's not just orthogonal, it's also normalized, so it's orthonormal. So the eigenfunctions of the momentum operator are orthonormal. Okay, we've proved that. Alright, so that's looking good for the momentum operator and its eigenfunctions and eigenvalues. Now in this case, I guess it's a bit implicit, but you can have virtually your eigenvalues can be virtually anything, any value for p, right? So if they're free waves, you know, they can have any value. You know, they just move along unrestricted. Okay, so that's for momentum. Now almost run out of board, but we can start at least on position. So what would a good position operator be? So if we represent position by x, you know, where is it along the axis, x-axis? So the position operator would then be x hat. So your position observable eigenequation presumably be something of this form. That's why the two here and here, the two eigenequations, I've put a rectangle around to emphasize their importance. So presumably this is what the position eigenequation would look like, right? So if this is the eigenfunction corresponding to the eigenvalue x dashed here, so you know, position operator, position eigenfunction, and position eigenvalue would just be x dashed. So then presumably this is the form it will take. So what that means is, it's a fairly simple suggestion. It's just this operator here, in effect, is just take the eigenfunction and just multiply it by x. Yeah, it's pretty simple. Right? You take the eigenfunction and multiply by x. That's all that's involved. But there are some mathematical complications. So, well, before I get into that, let me elaborate a little bit more. So, how do you interpret this? Well, these are your eigenfunctions, right, corresponding to this eigenvalue. So, in other words, this eigenfunction is the eigenfunction you get when the eigenvalue is x dashed. So, if you have this eigenfunction here, you know that the particle is at position x dashed. Okay, that's how you interpret it. But there's a bit of a complication in the sense that that psi function then tells the exact position of the particle, right, at x dashed. Now, from the Born, Max Born, his interpretation of wave functions is that when you square them, that gives you the probability density of where the particle is. Well, with this kind of eigenfunction, the particle is at an exact position. So the integral, think about it. You get a probability density. You integrate it over all space, and you get 1, right? Because the particle has to be somewhere. But if your wave function is one of these eigenfunctions for position, it gives an exact position for here. So what does that mean for the probability density function? So this eigenfunction says it will have 0 values at all positions except where at x dashed. When x equals x dashed, that's where the particle is, and this wave function will be 0 everywhere except at x equals x dashed. And you may be saying, aha, this sounds very much like the Dirac delta function, and you would be right. But I've run out of board, so I can't talk about that. But we're heading, in the context of the position operator, with these eigenfunctions that give an exact position, x dash, for the position of the particle, then these eigenfunctions here will need to take the form of a Dirac delta function. So next board, because I'm here on the fourth quarter of the board, I will talk about the eigenfunctions as delta functions, and I will talk about delta functions themselves. There's an appendix in the text, so I'll talk about the appendix as well, give you more information, greater knowledge of the properties of delta functions, because they play a prominent role when talking about the eigenfunctions of the position operator. Okay, but that's for next session.